Hello everyone, welcome back to my new video on AP Calculus AB. This is Unit 7 about differential equation. So first thing, what is a differential equation? So differential equation is just any equations that has a derivative in there. So for example, these three examples. First one, Newton's second law, F equal to ma. A is the second derivative of position respect to time. Second one is the LRC circuit voltage, and the third one is just a random differential equation. So there are mainly two types of differential equations. It's the ordinary differential equation, which it just uses the derivative we see right here, and there's also something called partial differential equation called PDE that has another type of derivative. Looks like this. It's called partial derivative. It's for multivariable functions or multivariable equations. And when modeling differential equations, they relate to a function of an independent variable and the function's derivative. And make sure to read what the rates that this keyword is the variable is relating to. And there should be always a constant. The differential equation should say something like some rates of something is directly proportional to something. And when there is a direct proportion, when it's proportional, there must be a constant k that shows it's proportional. So let's talk about an example. A puppy gains weight W. Our rates, so see rates, it acts on W. So we notice dW. Approximately inverse proportional, so we can say approximately inverse proportional, so k divided by something to its age, t. But what's the variable it's differentiating in respect to? Well, it's time, because the time is what's changing, and the weight is the output of that function. So let's move on. Let's talk about verifying solution for a differential equation. So basically, given a function y, we can solve the derivative, and we can substitute in to this derivative, and we can substitute the y in for this, and check if this equal sign makes sense. So let's work for this. So we got a function y equal to 4 natural log of x. Take the derivative of that is 4 over x. Let's see if that's equal to 2y, which is 8 natural log of x, divided by x natural log of x. Okay, so now we can simplify. Natural log of x cancels with natural log of x. So 4 over x, is it equal to 8 over x? The answer is no. So this is actually 4 over x is, so this function y equal to 4 natural log of x is not a solution for this differential equation. However, many differential equations have infinitely many solutions because the derivative of some constant k is equal to 0. So when you're integrating some function, let's say, actually let's just use smaller f dx, it's actually equal to big F plus c, because that's what we ignored. And now let's talk about slope field. So we can sketch a slope field by finding the derivative of a point. And usually this is dependent on x and y, so we can substitute the xy coordinate and into the differential equation. And now we have to draw a small segment on that point with the slope approximately equal to that derivative. And this is a slope field that's very well drawn. Of course, drawn by computer. But let's work on this example. Which differential equation satisfies this slope field? So let's look. At 0, 0, at 0, 0, the slope is equal to 0. So we can already eliminate D and E, because at this point, the slope is undefined. Now let's move on. So let's say we see that this path here, it's a linear path with a slope approximately equal to 1. So now let's just choose a point, say 4, 3. So let's choose 4, 3. And with the slope of 1, m equal to 1. Let's just try it. For a, dy dx, we substitute this coordinate in. That's equal to 7. That is not a solution. Second one, b, dy dx equal to 1. That could be a solution, so we'll mark a star on it. Third one, c, 3 minus 4 equal to minus 1, and that's not a solution. So only possible solution is b. And now let's move on. So reasoning using slope field. So when we have a slope field that starts at a certain point, we can trace a function that follows the direction of the slope field. And when you see this horizontal line here, it means that there's a horizontal asymptote, and the function can never reach there. And same thing for a vertical slope field. If it's purely vertical, then there's a vertical asymptote. So let's work on this. If the initial condition is 0, 1, it might be hard to see. It's right here. What's the range of solution to the curve of y equal to f of x for x is greater than or equal to 0? Now let's just trace. So start here. And go up, go up, go up, go up, go up, go up. And slope is gradually decreasing until we reach here. Right? This is exclusive. This is exclusive y equal to 4. So a is already eliminated. We see only b satisfies because this starts at 0, 1. And the slope is generally positive over that range, over that domain. So this only can be b. And let's talk about separation of variables. When we solve differential equation, we'll only solve some very, very simple differential equation. That these functions can be written as dy dx equal to f of x times g of y. It must be able to write as the product of two functions. One is with respect to x, one is with respect to y. And there are functions that's not differentiable, even though they look very simple. For example, this one, dy dx equal to x plus y. There's no general way for solving for this using our knowledge for calculus AB. And always make sure to double check if a function is separable, because it's through algebraic manipulation, and it's really easy to miss a differential equation that's separable. So what does separable even mean? Let's work for this. 3y squared plus 2 dy dx equal to 1. Well, it's already separated for you. Now this 1 we can say is f of x. 3y squared plus 2, consider that's g of y. It's okay that if you leave a constant 1 here, it's a function respect to x, it's just not there. X is just not there. So let's solve for this. So it's 3y squared plus 2 dy dx. What we want to do for this is that we can actually multiply both sides by dx. So let's write out the full thing. Can actually multiply both sides by dx. It's not a mathematical rigorous way to do this, but for this class, it's totally okay to move dy and dx apart. So we got dy and dx. We can now take the integral both sides, and let's see, that's y cubed plus 2y plus c1, the first constant on the right, equal to x plus c2. Now, we can simplify this. So that's y cubed plus 2y equal to x plus some constant c. Well, constant minus a constant is still a constant, so we just use c. And we give an initial condition that it has a point of minus 1, 1. So let's substitute it in and solve for this constant c. Y cubed plus 2 times y, 1 equal to x, which is minus 1 plus c. 1 plus 2 equal to minus 1 plus c. So c equal to 4. Okay, so we can solve the solution for this differential equation. So it's y cubed plus 2y plus 4. That's not x plus 4, since we're solving for this one. And it's not really beautiful because it's not a function y. The y doesn't appear only once. But it's okay because our goal is for solving the x coordinate when y equal to 2. Now we just need to solve for x. Let's substitute 2 into y. So 2 cubed plus 2 times 2 equal to x plus 4. X plus 4. What is this? A plus 4 equal to x plus 4. So x equal to a. And that is the solution for this. And lastly, let's talk about exponential models. You might have already learned this in your algebra class, but basically what's happening is that the rate of change is directly proportional to the size of the quantity. Note that directly proportional, meaning that dy dx equal to ky. When there's no directly, it may have some constant c plus to it. And so here is the derivation step. Dy dx equal to ky. And we can separate into this, take the integral both sides. We get this result here. And we just need to solve for y. And let's work on an example. Bacteria increase at a rate proportional at any time to the number of bacteria at a time. These were 800 bacteria initially, and they triple every 10 hours. What's the number of bacteria after 4 hours run to the nearest integer? So now, we need to analyze what it means. So after 10 seconds, 10 hours, then this, we can say, bacteria function t plus 10. When the time increased by 10 hours from right now, divided by the bacteria right now, this should equal to 3, because this value is 3 times of this value. So now let's solve for this. So initial condition C, actually let's use this y0 here, y0 e to the kx. X is in fact t plus 10, because we're substituting t plus 10 into that function. And now we have to divide by b of t. That's y0 e to the kt. this must be equal to 3. Y0 cancel out. So we got E of kt t plus 10 divided by E kt equal to 3. Let's simplify this. So that's E of kt plus 10k minus kt equal to 3. And E of 10k equal to 3. So we know that k equal to natural log of 3 divided 10. And now we can substitute this value back to our differential equation. Remember, y equal to y0 e of kx. So our function, b of t, y0 is the initial bacteria, which is 800. E of kt. K we already solved. It's natural log of 3 over 10. X, which is t, which is our independent variable. And now the question is asking what's the number after 4 hours. Now we can substitute b of 4. 800 e to the natural log of 3 divided by 10 times 4. And using a calculator, you can round it to the nearest integer, 1241 bacteria. Make sure to include the units. And now that's basically it, but I want to add another concept for solving differential equation. So in fact, we already solved many differential equations before. One fact is that this is a fact. In fact, this is a differential equation. F prime as x is a differential equation. So what this means that dy dx equal to y plus c. So in fact, when we integrate any function, that this final result function is a derivative of the function inside of this integral. So in fact, this is a differential equation. And now, that concludes my review for AP Calculus AB Unit 7. And please like and subscribe, and we'll see you next time.